In this video, we continue our discussion on chemical kinetics. We're going to look at some theories that allow us to understand the equations that we developed in our first video. And then we're going to look at reaction mechanisms, which are step-by-step processes taking reactants to products. And we'll conclude with a discussion on catalysts. Our starting place is collision theory and its relationship to concentration of species. The basic idea behind collision theory is that particles must collide in order to react, which is consistent with what we saw earlier. An increase in the concentration of reactant leads to a larger number of collisions and a corresponding increase in the reaction rate. The number of collisions depends on the product of the number of reactant particles, not their sum. And this is why the concentrations are multiplied in the rate law and not added. We can see this here for a simple A-B collision. If we have two particles of A and two particles of B, we can have 4 collisions leading to products. If we add another A, then we have 6 collisions occurring. And if we add another B, 3 A's and 3 B's, we end up with 9 collisions occurring. This accounts for our product relationship, not a sum relationship. Our next concept we're going to look at relates to temperature, and this is activation energy. As we saw earlier, if we increase temperature, we increase reaction rate, and this is underpinned by 2 factors. We know that as we increase the temperature of a system, the molecular speeds increases, as we saw back in chapter 5. If we have an increased speed, we're going to have more frequent collisions, and those collisions will be more energetic. The important thing to think about here is effective collisions. These are the ones that actually lead to product. And these 2 factors, activation energy and molecular orientation, are ones that determine what are effective collisions. Collisions must occur with enough energy to allow bond breaking to occur. We're going to have to get over something called an activation energy. Also, they must collide in the correct orientation. So here we see, a high jumper jumping over a bar. We can think of molecules in the same way. We can go from reactants to products. The energy difference between reactants and products is given by delta H. But in order to get there, the reactants have to proceed through an activated state. We're going to see later on, we're going to call this a transition state. So collisions must occur with enough energy to get up to the activated state, where the bonds are being broken, and then make our way down to the products. And in general, the activation energy depends on the direction you're going. So if you're going from reactants to products, you'll have the activation energy for the forward direction, here shown as E sub A forward. If you're going from products back to reactants, in this case, you'd have a larger activation energy. You have EA reverse. So it's not only that you have to have the correct energy, but you also have to have the correct orientation. For a collision between particles to be effective, you have to have the right direction of the molecule orientation. Atoms that are going to be bonded in your product must be making contact during the collision. You don't want them on the backside of the collision interaction. We have something called an orientation probability factor, P, which is a fractional value, and it's specific for each reaction, and it's related to the structural complexity of the reactants. Generally, it's the ratio of the effective oriented collisions relative to all possible orientations during the collision. The more complex the molecular structure, generally, the smaller the p-value is. Here we can see an example for this. So now we're going to take NO and nitrogen trioxide, collide them together as reactants to produce 2 molecules of nitrogen dioxide. So it's a simple oxygen atom transfer from the NO3 to the NO. In this case, for the collision to be effective, the oxygen on NO3 must collide with the nitrogen on NO. You can see that on the right-hand side with the Lewis dot structures. So the oxygen has to be colliding with the nitrogen. On the left-hand side, you can see a series of different collisions. In this case, the blue represents a nitrogen atom, the red represents an oxygen atom, and the only collision that is effective is the one at the bottom, where the nitrogen atom on nitric oxide collides with an oxygen atom on nitrogen trioxide. All the other orientations are ineffective. And so from this, you can see that very often the collision probability is actually relatively low, even for simple systems like this. Transition state theory pulls this all together. An effective collision between particles leads to the formation of what we call a transition state, or activated complex. This transition state is not a stable molecule, but it's the intermediate that exists in fleeting time as we go from reactants to products. The transition state is an unstable C species, and the bonds are not full bonds. They're not normal full two electron bonds. They are partial bonds. This is a transient species. It's transitional between reactants and products. As a general rule, we cannot isolate transition states. We can't make them as chemical species. It only exists at a point on the maximum potential energy. The energy required to form the transition state, that is the activation energy. So next we're going to look at a reaction energy diagram which plots out the potential energy change as we move from reactants through transition state onto products. So we're going to look first at the reaction of bromomethane, BrCH3, with the hydroxide ion, OH. OH collides with bromomethane to produce bromide plus methanol. The transition state contains partial bonds, which are shown here. So if you look at this transition state, which is in between the reactants and the products, you can't isolate that. And now it makes sense to you because if you look at the Lewis dot structure, you can see carbon has 5 bonds. And we know that in all of your stable organic compounds, carbon has 4 bonds. So that tells us that the carbon-bromine bond and the carbon-oxygen bond are only partial bonds. There's not enough electrons to make a full bond to either one of these species. So this molecule cannot be, this transition state or species cannot be isolated. Here it's shown as having a trigonal bipyramidal shape, but again, it's a fleeting species, not having any significant lifetime. Now, what we can do is we can depict a reaction energy contour, and that's at the very bottom. Let's start there. We can have on the y-axis the potential energy, and on our x-axis we'll write out reaction progress. So we're starting off with methyl bromide plus hydroxide. Then as those two species come together, the energy rises up because we're breaking the carbon-bromine bond. That's requiring energy. And as we rise up, we get the top of a little hill, and the top of that hill is the transition state. That's the five bonded intermediate system. And then once this forms, we immediately roll down the backside, off to the right, where we end up with our products, bromide plus methanol. Right above the reaction contour, then, we can see pictures, ball and stick figures or Lewis dot structures that represent this. And you can see that in the middle, we have our transition state. That transition state has carbon with 5 entities around it. 3 of them are fully bonded, that is the 3 carbon-hydrogen bonds. But the carbon-bromine bond and the carbon-hydroxide or the carbon-oxygen bond are both partial bonds. That's not a stable species. And in the top graph, we see the electron distributions for these species, which are calculated from quantum calculations. And you can see that the carbon-bromine has electron density that's less than a bond on the the transition state. Now let's look at two other reactions that occur, and let's look at this reaction coordinate model for these two systems. The first reaction on the left is two NaCl molecules colliding to form two molecules of nitric oxide, NO, plus one molecule of chlorine. So in this case, you can see that the nitrogen-chlorine bond in both the reactant molecules have to break, and then we're going to form a chlorine-chlorine bond, which will be generated to produce our product. Right above this, we see the reaction profile. This reaction is endothermic, going from the two NOCl. We see the delta H reaction is positive to give us our 2NO plus our molecular chlorine. So this reaction is endothermic. It's a decomposition reaction. In order to get to this product, however, the molecule, the nitrosyl chloride, the NOCl, does not simply fall apart. If it's at low temperature, it'll be stable. If we heat the system up, however, it begins to decompose. Because as we heat it up, molecules can go up to the transition state where the nitrogen-chlorine bonds begin breaking and the chlorine-chlorine bonds begin forming, and then we roll out the backside. We see we have two molecules of NO plus one molecule of molecular chlorine. On the right-hand side, we have the reaction of nitric oxide plus ozone to give NO2 plus O2. In this case, we're breaking one of the oxygen-oxygen bonds in ozone, and we're forming an oxygen-nitrogen bond in NO2. This reaction is exothermic. NO reacts with O3, it's downhill to NO2 plus O2. This turns out to be a very important reaction in the stratosphere, and is one of the reasons that supersonic aircraft flying in the stratosphere can destroy molecular ozone in that region. So you can see that we're breaking the oxygen-oxygen bond in the transition state, and we're forming the nitrogen-oxygen bond in the transition state. So let's account for the effect of temperature on reaction rate. Temperature has a dramatic effect on reaction rate, and as a general rule of thumb, very rough rule of thumb, for many reactions, if we increase the reaction by approximately 10 degrees Celsius, the reaction rate doubles or triples, very roughly. And we can look at the hydrolysis of the ester ethyl acetate. So if we do this hydrolysis reaction, here we have 4 experiments where we have the same ester concentration and the same water concentration. And we're changing our temperature from 288 up to 318 Kelvin. You can see that the reaction rate is increasing. And since the concentrations are constant, that tells us that if the rate is increasing, the rate constant must be increasing. That's what's driving the reaction. The reaction rate and the rate constant increase exponentially with temperature, and that's shown on the graph at the right. You can see rate constant as a function of temperature goes up exponentially. How do we account for this? Well, temperature affects both collision frequency and collision energy, as we said before. For collision frequency, if we increase the temperature, this increases the kinetic energy of the particles, but it also increases their speed, so we have more frequent collisions. And if we have more frequent collisions, we're going to have faster reaction. Also, as we increase the temperature, those more energetic collisions can get us over the activation energy. And as a general rule, the fraction F of collisions that have energy greater than the activation energy is given by the following equation. F is equal to E to the minus E sub A over RT, where R is our gas constant, and this is going to be in units of energy. So it's going to be in joules per Kelvin mole. At higher temperature, the fraction of collisions with sufficient energy equal to or greater than the activation energy, and that affects the reaction rate as well as the collision frequency. So here we see a plot which looks like the Maxwell-Boltzmann distributions we saw from chapter 5, but it's a little bit different. We're looking on the y-axis at the fraction of collisions F as a function of the x-axis collision energy. So this is a little different. In chapter 5, we were looking at molecular speeds. Now we're converting this to an energy value. So you can see at T1, the fraction of molecules that have an activation energy above the activation energy E sub A is given in that purplish region, and it's a small value. As we increase the temperature to T2, the curve shifts to the right. The fraction of collisions is now shown to be larger. So here in this table, we're looking at two different things. We're looking at the effect of activation energy E sub A on the fraction of collisions that are effective, and also the temperature and its effect on the fraction of collisions that are effective. So first, the upper three rows show constant temperature 298 Kelvin, and we see three different activation energies, 50, 75, and 100 kilojoules per mole. So these are very high activation energies. And in this case, the fraction of collisions at 298 Kelvin is actually quite low. And you can see that this number will decrease as the activation energy goes up. So as we increase the activation energy, the fraction of collisions that can make it over the barrier becomes smaller. At 50 kilojoule per mole, we have 10 to the minus 9 fraction of our collisions are effective, but at 100 kilojoule per mole, it's 10 to the minus 18. Now the lower three rows show us for a given activation energy, in this case 50 kilojoule per mole, the effective temperature on the fraction of collisions that are effective. So we're going from 25 to 35 to 45 Celsius. And as we increase this temperature, you can see the fraction of collisions that are effective goes up. And in fact, it roughly doubles for every 10 degrees Celsius. So from 25 to 35, the fraction of collisions that are effective roughly doubles. And then from 35 to 45, it roughly doubles again, consistent with that rule of thumb we talked about earlier. So smaller activation energy or higher temperature, larger fraction of effective collisions, larger rate constants, higher reaction rate. Now, we can pull this all together with an equation that's called the Arrhenius equation. And this allows us to actually calculate the activation energy. In general, we measure our reaction rates from which we can derive rate constants. Using this, we can figure out the activation energy. Now, the Arrhenius equation shown here is shown in bold with 3 stars, so this is an important equation that you should remember because you will use this. The rate constant is equal to A, which is called the frequency factor or the Arrhenius frequency factor or the pre-exponential factor, times e to the minus E sub A, that's the activation energy, over RT. R is the gas constant and T is the absolute temperature. So R in this case will be in units of joule per Kelvin mole if our activation energies are in joules per mole. The frequency factor, the A, that pre-exponential factor, can be estimated as the product of the collision frequency, Z, that is how often molecules collide with one another, times that probability factor. Remember P, we talked about the orientation factor, the fractional value. So A is equal to P times Z. Now, we can take that equation, K is equal to A e to the minus E sub A over RT. We can take natural logs of both sides, and then the natural log of the rate constant is equal to the natural log of the pre-exponential factor minus E sub A over RT. And if we do this at 2 different temperatures, then we end up with the lower equation, which will be a useful one later on. The natural log of the ratios of the rate constants is equal to the activation energy divided by R times 1 over T1 minus 1 over T2. So that's a useful equation for you to remember. So if we take that equation, that tells us that if we plot the natural log of the measured rate constants as a function of 1 over temperature, the intercept, the y-intercept, will be the natural log of the pre-exponential factor, and the slope of the curve, or the slope of the line, will be minus E sub A over R. Now we're going to look at reaction mechanisms. A reaction mechanism is the sequence of individual reaction steps that are along the pathway to get to our final product. Very often, molecules don't simply collide and produce product. They'll go through a series of individual steps. And the individual steps of the reaction mechanism are called elementary steps because each one describes a single molecular event. Each elementary step then has a molecularity, that is, the stoichiometric coefficients for that elementary reaction. And the number of reactant particles involved in this elementary step is called the molecularity. That's the stoichiometric coefficients. So here is where we tie back to what we said earlier. Earlier we said we can't deduce the rate law in general from the stoichiometry, but for an elementary step, we can deduce the rate law from the reaction stoichiometry. The reaction order equals the molecularity for an elementary step only. Here is a table showing rate laws for general elementary steps. If A goes to product, the molecularity is unimolecular, so the rate law is K times A to the first power. If two molecules of A collide to give product, it's a bimolecular system. The rate goes as the square of A. If A plus B goes to product during our elementary step, it's bimolecular. It's first order in A, first order in B, second order overall. Now your book mentions 2A plus B going to product as termolecular. These are so rare as to be completely insignificant, and you should ignore this. So there are not significant termolecular processes because simultaneous collision of three molecules is exceedingly rare. The rate determining step of a reaction, if we have a series of molecular steps, turns out to be the slowest process. So if we have a series of elementary steps, each one can have a different speed or a different reaction rate. The one that turns out to be the most important in determining the overall speed of the reaction is the rate determining step. Sometimes we call this the rate limiting step. In this case, then, the rate law for the rate determining step becomes the rate law for the overall reaction. So let's take an example. Let's take nitrogen dioxide reacts with carbon monoxide to give nitric oxide, NO, plus carbon dioxide, CO2. The proposed mechanism has two steps. In the first, so this is not a simple oxygen atom transfer to CO. The first step in the proposed mechanism is two molecules of nitrogen dioxide collide to give nitrogen trioxide plus nitric oxide. And this is known to be a very slow process. And it's proposed that this is the rate determining step. The second step is where nitrogen trioxide collides with carbon monoxide to give NO2 and CO2. This is the fast step. And of course, NO2 as a product is also one of the reactants. So NO3 is what we call a reaction intermediate. This is a substance that is formed in one step, but it's also used up later on. So it's not generated as a product and it's not necessary as a reactant, but it does exist as a stable intermediate. It's not a transition state. It's a reaction intermediate. Now we find out that the observed rate law is equal to the following. Rate equals rate constant times nitrogen dioxide concentration squared. You notice here that carbon monoxide isn't even in the rate law. It's not in the rate law because it only participates in a very fast step. The important step is formation of nitrogen trioxide. In general, a A valid reaction mechanism has to meet the following three criteria. First off, the elementary steps must add up to give you the overall balanced reaction. That's an obvious necessity. Second, the elementary steps must be reasonable. Generally, they're bimolecular or unimolecular steps. They don't involve really complicated things like termolecular steps. And then the mechanism must correlate with the observed rate law. A mechanism, though, is only a hypothesis. We can't prove that it is correct, but if it's consistent with the data, we can use it to predict future results accurately. Then it becomes a useful model. So let's go back and let's look at another reaction. That's the reaction of nitrogen dioxide with fluorine to give NO2F. So the overall reaction 2NO2 plus F2 gives 2NO2F is shown here. It's known to have an experimental rate law of rate constant times nitrogen dioxide times fluorine, both first order in both reactants. Notice that even though there's two stoichiometric coefficient on the nitrogen dioxide, it's still first order in both. So this is experimentally determined. So how do we account for this? Well, the accepted mechanism is as follows. In the first step, nitrogen dioxide collides with fluorine to form NO2F and a fluorine atom. This is a slow process. You have to break the fluorine-fluorine bond. This is the rate determining step. And then this is followed by a fast step where a fluorine atom combines with another NO2 molecule to form NO2F. So overall, then we end up with two NO2s reacting with F2 to give two molecules of NO2F. The elementary steps sum up to give the overall balanced equation, so that's good. Both steps are bimolecular, and they're both reasonable. And so the rate law for the first step would be the rate constant times the concentration of NO2 to the first power times the concentration of F2 to the first power. And then the second reaction, which is the fast one, has its own rate constant times the concentration of NO2 times the concentration of fluorine atoms. Step one is the slow step, and thus rate 1 correlates with the overall observed rate. So this mechanism is therefore reasonable. It meets all three criteria. And we can go back to our earlier reaction. Two molecules of NO react with O2 to give 2NO2. And we saw that that had an experimental rate law that turns out to be the rate constant times the nitric oxide concentration squared times the oxygen concentration. The mechanism is proposed. Have NO colliding with O2 to give NO3 as our fast reversible step. And then nitrogen trioxide reacts with nitric oxide to give 2NO2, which is the slow rate determining step. If we add these two steps together, we get our overall reaction. So the elementary steps sum to the overall balanced reaction. That's good. Both steps are bimolecular and therefore reasonable. That's good. We have our three rates because now we're not just going forward in our first reaction, we can also have the reverse process. So rate 1, going forward on step 1, is K1 times nitric oxide concentration times O2 concentration. We can go backwards. Rate 1 in reverse is the reverse rate constant times the nitrogen trioxide concentration. And then rate 2, which is slow, and that's the rate determining step, that rate is equal to K2 times the nitrogen trioxide concentration times nitrogen monoxide or nitric oxide. Now notice, let's just pause here for a second. We have a fast reversible reaction. That's not rate determining. Then we have a slow rate determining step. That step should, the molecularity and the rate law for that should determine the rate for the process. In this case, you might say rate 2 would equal the overall rate. It would equal K2 times the nitrogen trioxide concentration times NO. But notice nitrogen trioxide is only an intermediate. And in fact, its concentration might be quite low. And so we're going to need to determine what that is by a rearrangement. So what we can do is we can go back to step 1. We notice that once this reaction gets rolling, if it's fast and reversible, the forward rate will equal the reverse rate because it's fast and reversible. So that means K1, that first rate constant times the nitric oxide concentration times the oxygen concentration, will equal the reverse rate constant times the nitrogen trioxide concentration. And we can rearrange this to determine the nitrogen trioxide concentration. So let's do that. Nitrogen trioxide then would equal the forward rate constant divided by the reverse rate constant times the nitric oxide concentration times the oxygen concentration. And we can plug that value for the nitrogen trioxide concentration back into the rate expression for the second step. And if we do that, we end up with this equation. Rate 2 equals K2 times the product for the NO3, which is K1 divided by K2 times nitric oxide times O2. And we can lump K2, K1, and K minus 1, excuse me, there's a mistake on here. That should be K minus 1 on the bottom, into one overall rate constant. And then the NOs will come out as a product. And so now NO will be squared, and O2 will be to the first power. So I'll correct that error in the proper slides that you'll have. But the rate constant K then will be equal to K2 times K1 divided by K minus 1. For any mechanism, only reactants involved up to and including the slow step appear in the overall rate. Now what we can do is we can take what we learned about activation energies and we can combine it with mechanisms. So now let's look at those two reactions we just discussed. Let's look at reaction energy diagrams, or these reaction progress diagrams for the reaction of NO2 with F2. So this is on the left-hand side. 2 molecules of NO2 react with F2 to give our product NO2F, 2 molecules of this. As this goes forward, there are 2 transition states because there are 2 steps in the mechanism. So our first step is the rate determining step with the highest activation energy and the slowest reaction. And that first step is that step that breaks the fluorine-fluorine bond. So our intermediate is the NO2F plus F plus NO2. And then we have a much smaller activation energy for fluorine to combine with NO2 to form our product. Likewise, for our second reaction, the reaction of nitrogen with O2 to form our product, we see that our initial step is the fast step. That's the one that was reversible to form nitrogen trioxide plus NO. That's a fast and reversible process. But then the slow step is the nitrogen trioxide then reacting with nitric oxide to give your NO2. So we see that the second step is the larger activation energy step. Finally, we're going to look at catalysis and catalysts, which are species that speed up a reaction. And you can think about this in a very simple way. You know that honey has been found in many ancient archaeological sites. So, for example, in King Tut's tomb, they found honey. And the oldest honey discovered was in the country of Georgia. In some underground pottery, there were traces of honey found that's still edible. So that tells you that honey is a very stable substance. It doesn't spontaneously convert. But if you, for breakfast, decide to put honey on your pancakes and you eat it, that honey will be very quickly converted into energy in a matter of hours rather than a matter of millennia. And that's because your body has proteins. These are catalysts that speed up the reaction. So a catalyst is a special type of a substance that participates in the reaction but doesn't get converted itself. It's a substance that increases the reaction without itself being consumed in the reaction. And the way this works is the following. In general, a catalyst provides an alternative reaction pathway that has a lower activation energy than the uncatalyzed reaction. And in some cases, it's a much lower activation energy. Catalysts speed up both the forward and the reverse reactions, so they're neutral in their participation. And catalysts don't affect the overall enthalpy of reaction or the overall yield. All they do is change the kinetics. And the way they work is illustrated here. In general, if I have A and B as reactants to go to some products, we can see here's an energy diagram, and the orange line is the reaction of A plus B without a catalyst going up to a high transition state star and leading down to products. If we add a catalyst, then we go through the blue line, and you can see this might involve multiple steps here, but in this case, the transition states for the catalyzed reaction are much lower. Therefore, the reaction will be much faster. An example of this is a homogeneous catalyst. A homogeneous catalyst exists in the same phase as the reactants. So we can consider the decomposition of hydrogen peroxide in water to produce water plus oxygen. This reaction is usually relatively slow in the absence of light, which is why when you buy a hydrogen peroxide bottle, it's usually got a dark opaque plastic on the outside. But if you add a salt to it, like sodium bromide, you can speed up the reaction. The bromide doesn't convert, ultimately. All that happens is the hydrogen peroxide decomposes. And it proceeds by the following mechanism with bromide as the catalyst. The bromide initially interacts with hydrogen peroxide and some protons, some acid, to produce a little bit of aqueous bromine molecules. And then the aqueous bromine molecules further react with hydrogen peroxide to produce bromide and regenerate protons. So it's a two-step process. And if you add all the species there, you notice that the bromides will cancel, the molecular bromines cancel out, and the only thing left over is your 2 molecules of hydrogen peroxide producing 2 molecules of water plus 1 molecule of oxygen gas. Bromide, in the presence of protons, is the catalyst, and bromine is the intermediate. And you can see on the on the left-hand side, you have hydrogen peroxide. If you drop in the clear sodium bromide salt, you get a short-term production of bromine, which is the slight brown color, but that fades away very quickly, and you end up with your ultimate product, which is sodium bromide in water with a little bit of extra oxygen in the water. A heterogeneous catalyst does the same thing as a homogeneous catalyst, but heterogeneous catalysts, just like heterogeneous mixtures, are in different phases. So here the catalyst is in a different phase than the reaction mixture. And very often these are solid metals or metal oxides. So the example that we see here is something called hydrogenation. That is where we add hydrogen to a carbon-carbon double bond like ethylene or ethene. And when the molecules collide on the surface, the metal surface allows the atoms to break up temporarily. And when once they break up, they can move around on the surface, recombine to form your more stable product, ethane. An important set of catalysts are like the ones we talked about earlier, the ones in your body. And these are biological catalysts. An enzyme is a biological macromolecule, and it's usually a protein that acts as a catalyst. A small part of the enzyme's surface is something called the active site, which is a region that has a shape based on these amino acid side chains in the protein that allows the molecules to fit in quite nicely, and the substrate is the reactant that binds into that site and then begins its chemical reaction pathway. It's often shown as this lock and key model, where the gray represents your protein or your enzyme. Your substrates fit into the lock and key. They're held there, and you generate your product. So the lock and key model visualizes the enzyme active sites and their appropriate shapes. And so it's very specific to a particular substrate. That ends our discussion on chemical kinetics.